So we're going to continue on taking pressure into account. We're going to start talking about wind. Uh, Everybody's got a little bit of interest in wind just because, hey, you don't want to be outside blowing around too much. So we're going to learn why. Why does the air move from one direction to another? Why does it pick up, get really strong, real lot of wind or very little wind? Or if you think about it, as you go up in the atmosphere, there's more wind. So why is that? Why is there more wind higher up, like on the top of mountains and all, than there are down towards the ground? So let's learn a little bit about that right now. So what forces control the speed and direction? Wind is something you need to understand has two components. It has a speed, so how fast is it going, and where is it coming from? Both are equally important. So very simple definition for wind. It's the local motion of air measured relative to Earth's surface. So in other words, it's a piece of air moving from one place to another. Along what path? So we've talked about forces that push pull on molecules, on objects. Well, that's what makes the wind again. Here we go back to force. So it's this simple mass times acceleration. Acceleration is a change in speed, change in velocity. So what are the forces that act on wind? And we're going to go into some a little detail with these. Air pressure gradient, centripetal force, Coriolis effect, friction, gravity. So let's start simplest one, and probably the one that has the biggest impact is pressure gradient. All right, so if I have pressure that is higher in one location than another, we know we have low pressures and high pressures. Air is going to always want to move from the high pressure to the low pressure. What air is doing, it's trying to equalize the pressure. It wants the same pressure everywhere. Can't happen, but it will work to do that. And it will always blow from high pressure to low pressure. So if I have, notice the isobars up here at the top. Not We go from 1016 to 1028 over a pretty relatively short distance. Down here we go from 1020 to 1028 over a wider distance. The wind is going to blow from the 1028 direction to the 1016 direction. And because these isobars are closer together, think of it as an increasing slope, if you will, to the air. Air is going to want to go tumbling down that slope faster and faster. So the more isobars over a shorter distance, the stronger the pressure gradient, the stronger the wind's going to be. The further apart they are, the lighter that wind will be. Second force, it's an interesting one, centripetal force. So what makes objects move in a curve? You ever go around a curve in your car or on a bicycle? You're always trying to be pushed out away from staying on that curve. That's why you see cars spin out on curves when it's slick. The force that keeps you on that curve, allows you to go around it, is centripetal force. Same thing happens to air. When it is going in a circle around low pressure or high pressure, it's centripetal force that makes it go in that. Another component. The next one is because we have a rotating Earth. Yeah, our Earth does not sit still, it rotates. Because it does that, it means that a part of the Earth moves faster than another part of the Earth. Think about it. If you lived right at the North Pole, the Earth is hardly rotating because it doesn't spin much up at the North Pole. Now, if you live at the equator, you're moving pretty doggone fast along us. You've got to cover 23,000 miles in a day. At the North Pole, you're not covering any. So that generates another force called the Coriolis effect. Here's a great example of it. You have a point over the central United States. See a north-south line. North-south line stayed the same as the Earth rotated. But notice the change in the axis of that line, where everything was right along to the east here. Now that to the east, is further to the right. In the northern hemisphere, the Coriolis effect, or force, always acts to the right. In the southern hemisphere, it acts to the left. And you can see it here. And there is a greater deflection the further north you are. The closer to the equator, you have almost none. So there's very little Coriolis force at the equator, but tremendous Coriolis force higher up towards the poles. Friction. We all think of friction as when you're pushing along a surface, pushing an object along, trying to make it slide. Sometimes it's really, really hard. Sometimes it's very easy. If you're doing it with snow cover on ice, man, things slide real nice. If you're doing it on a really rough surface, on a hillside, they don't slide so well. That's the same that happens with air. If air is moving across a smooth surface, it moves very easily, and that smooth surface might be water. If it's moving across land, land has little bumps in it, hills in it, they're going to slow it down. And when you go up in the atmosphere, you have eddy viscosity, it's called. What it is turbulence in the air. If you're flying along, you're bouncing in an airplane or whatever, that turbulence, that is friction in the air. Gravity. Gravity pulls everything down to Earth. It's what keeps our atmosphere in place. It pulls the air down. It keeps us from flying out into space. And gravity actually has two parts to it because the Earth rotates. If the Earth didn't rotate, it would just be gravity pulling us in. But the Earth rotates. Something has to be holding you on Earth as far as rotation goes as well. That's the centripetal force. So gravity on Earth is a combination of the gravitation between objects and centripetal force. So now we've covered all of these things, and every one of them relates to where the wind's going to go. So let's start with the simplest one. What keeps the air parcel from moving out into space? Well, what keeps that is, think about it, the pressure went from the surface 1,500 meters up, it dropped 150 millibars. So there is a tremendous pressure gradient in the vertical. That pressure gradient should be shooting all these air parcels out into space quickly. No atmosphere, we're done, right? But it doesn't. Why doesn't it? It is because of gravity. Gravity pulls everything back down, and there's a balance called the hydrostatic equilibrium between the pressure gradient force upwards and the force of gravity down towards the Earth. What that means is the air stays. We don't lose it. Yes, vertical motions can still take effect. We can still move an air parcel up or down, but it's at a continuous speed. It's not changing speed. That is what hydrostatic equilibrium means. There's another wind we term. If you look in the upper atmosphere, you're going to see winds parallel to the contours or isobars. When they do that, how did they do that? What causes that? Well, in that case, there's no friction, so we don't have to worry about friction in the upper atmosphere too much. So there's two forces. You have the horizontal pressure gradient, so everything wants to go from high pressure to low, so it starts out with that. But as the air parcel is moving, it is being pulled to the right by the Coriolis effect. And eventually, it reaches equilibrium where the pressure gradient and the Coriolis effect are the same. They balance each other out, and the air parcel will just move in a parallel line straight along between the contours. That is called the geostrophic wind. It's the simplest wind you can get. Two forces in balance moving the wind along. Basically a straight line wind. Now, sometimes we have low pressures and high pressures, and the wind goes in a circle. All we have done is added one more component, centripetal force. Everything else has stayed the same. So there's a pressure gradient, there's a Coriolis effect, and we've added the centripetal force. Centripetal force causes these things to go in a circle. If you didn't have it, you would be back to geostrophic wind. Finally, we add friction. When you're down close to Earth, near the surface, friction becomes a significant component. What happens? It slows wind speed down. Well, if the wind's not blowing as much, pressure gradient is still the same, but the Coriolis effect is not. Because the wind speed is not moving as fast, the Coriolis effect is less. You wind up with winds blowing outward from high pressure and inward to low pressure at an angle. Instead of being directly from high to low, they'll be at an angle. But they will blow towards low pressure near the surface of the Earth and out from high pressure. That is all due to friction. And here you can see a typical map of that. All right, we talked earlier about pressure and how winds, if winds at the upper levels of the atmosphere influence winds at the lower levels. So let's take a look at upper level here. We have much stronger winds coming into this area than going out of it. The air is getting piled up in here. What's it going to do? Instead of going up out of the atmosphere, it's going to go down. It's going to sink. And then down here, well, you can't have a whole bunch of air here. It makes a high pressure though, doesn't it? But you're going to push everything out. High pressure says everything's got to move out from it. So you wind up with divergence there. Now, opposite. Low pressure. Air is rising. We have divergence aloft and convergence at the surface. So air is coming together, pushing the air to rise. These are conditions where we get low pressures, we get rain, snow, bad weather. You want rising air for that. So let's take another one here. We have sea breezes, lake breezes. If you go to Lake Erie, you get a lake breeze coming off the lake, especially in the springtime. So what happens is, well, you have air that wants to move from the lake to the land in the summertime, in the winter as well. But and that air will move pretty quickly across the smooth lake surface. Now it's going to hit the mountains and rough terrain. It'll slow down. When it slows down, air piles up. We wind up with rising air. That is why when a sea breeze hits or a lake breeze occurs, you wind up with showers and thunderstorms sometimes along it. Lake effect snow is a classic example of that in the wintertime. So let's go here. I want to show you a little bit on an actual weather map. Here is the current conditions. Notice the low pressure right here over South Dakota. Notice the winds. Look at the pressure gradient here. Several knots of wind right here, 20 knots of wind. And notice how they move towards low pressure. They're moving in. High pressure over here. What do? They move out. The winds are moving away. Very light winds in here. So this is the effect that friction has on the wind. Now let's move a little bit aloft. I want you to see pretty tight contours here. Strongest winds are in this area. And you'll notice the centripetal. But you also have a great geostrophic wind right here. Notice how it goes parallel to it. There isn't as much friction at this level. So, and finally, if you even go higher up, you have less friction, more parallel to the contours. So this is what you've learned this week. Now you can go out and explain why that wind's coming from the east or the southeast, right? But this is what you're going into. If you were writing a forecast, one of the things you need to know is where the air is coming from. If I have air coming out of Canada down to where I am, I'm going to get colder, right? If I have air coming up from the Gulf of Mexico, it's going to get warmer and more humid. So I want to know where the air is moving, and this is how we go about doing that. So let me know if you have any questions with this.